Lecture 9 in our course. So today we start a new chapter. This is called inner product spaces. So far we have studied how to solve system of linear equations by using Gauss elimination, and we know the algorithm to find all solutions of any system. Yeah, we also know how to test whether a solution exists. And if the solution exists, how to find a particular solution, how to find fundamental solutions of homogeneous system of linear equations. And then we introduced vector spaces. The purpose of introducing vector spaces was that in a matrix, with a matrix, we have four very basic subspaces which are used in applications: the row space of a matrix, the null space of a matrix, the column space of a matrix, and the left null space of a matrix. So these four subspaces, yeah, they are interrelated, and one interrelation we have already found, which is the rank nullity theorem. Yeah, the rank nullity theorem. We have done it for linear transformations, we have done it for matrices, but for matrices it says that we have the row space of the matrix and the null space of the matrix. Yeah, these two spaces, they are living inside the domain. Okay, and the column space of the matrix is living in the codomain, and the left null space. Okay, left null space is really the null space of A transpose. Okay, and we showed that the dimension of the row space, which is called the rank of the matrix, and the dimension of the null space, okay, which is called the nullity, yeah, they add up to the dimension of the whole space in which they are living. Yeah, dimension of the row space and dimension of the null space is equal to dimension of the space in which they live, and which is the number of columns of A. So this is the rank nullity theorem, and we also proved if you have two subspaces, then we know the dimension of the sum of those two subspaces. Yeah, the dimension of the sum of the subspaces. So we did this, that if I have a big vector space V and we have two subspaces, yeah, W1 and W2, then their sum lives inside V. The sum of these two subspaces is really the sum of all the vectors V plus V, where U is in W1 and V is in W2. Okay, and we proved this formula, that dimension of the sum, is equal to the sum of the dimensions minus the dimension of the intersection. So if you apply this formula on the null space and row space, it says the dimension of the sum of the null space and row space is dimension of the row space plus dimension of the null space. Yeah, but that is already equal to the dimension of the whole space, and therefore this intersection has to be 0. Okay, this intersection is actually 0. The row space of the matrix and the null space of the matrix, they intersect only in the 0 vector. Okay, and the null space of A is collection of all vectors, so that Ax equal to 0. But Ax equal to 0 means, yeah, I write the row vectors of A. There are m row vectors of A, and x is a typical vector in the null space, and this is equal to 0. So this means that A1 dot x equal to 0, A2 dot x equal to 0, etc. So therefore, every vector in the null space, if I take any vector in the null space, then it is perpendicular to every row vector. Is that clear? Yeah. every vector in the null space is perpendicular to every vector in the row space. The rows, they are perpendicular to the rows, and if a vector is perpendicular to two vectors, it is also perpendicular to any linear combination. X dot, say alpha ai plus beta aj, yeah, this is equal to alpha alpha ai dot x plus beta aj dot x, but x is perpendicular to ai and x is perpendicular to aj, so this is equal to 0. That means every vector in the null space is perpendicular to every vector in the row space. So if we are living in three-dimensional space and my row space is a plane passing through origin, let's say xy plane, the null space has to be perpendicular. It has to be all vectors on the z-axis. This is forced. The null space is forced to be the z-axis if the row space is the xy plane. This is because of the relation between null space and row space, that the dimension of the null space and dimension of row space, they add up to the dimension of the whole space. We are in three-dimensional space, so their sum of their dimensions is 3, but then there is nothing common except the zero vector in the null space and row space. There's only one vector which is common between them, namely zero vector, and every vector in the null space has to be perpendicular to the row space. So if the row space is xy plane, then the null space has to be the z-axis. Okay, so there is geometry going on behind these subspaces associated to a matrix. Yeah, that's the relation between null space and the row space. And if you go to the right, that is go to the codomain, then we have the column space and the null space of A transpose. Column space of a matrix is really the row space of A transpose. So it's the same argument says that the other two subspaces, namely column space of A and the null space of A transpose, they are also intersecting only in the zero vector. The column space of A and the null space of A transpose, they also intersect in the zero vector only, and every vector in the null space is perpendicular to every vector in the column space. Yeah, so the two subspaces, row space and null space, they are perpendicular, they span the whole domain. Yeah, similarly the column space and null space of A transpose, they are perpendicular to each other and they span the whole codomain. Yeah, so we want to now introduce these geometric notions which we already observed among the row spaces and null space, etc. of a matrix. We want to introduce in an arbitrary vector space. Yeah, so dot product is known to us for vectors in Rn, and we want to extend this to arbitrary vector space. Okay, and the purpose is to introduce geometric notions. So length of a vector is a geometric notion. Angle between vectors, yeah, that's a geometric notion. And in your electricity and magnetism, you deal with lots of vectors, but in order to make measurement, you have to take the length of the vector. You want to know angle between vectors to calculate actual force applied to some moving particle, because we know that when a force is applied to a moving particle, only the component of the force which is in the direction of the movement of the particle is responsible for the motion. The other component, which is perpendicular to the direction of the movement, has no effect on the motion of the particle. So we need to decompose vectors as sum of two perpendicular vectors or sum of three mutually perpendicular vectors in R3, etc. So in vector spaces, we want to now introduce geometric notions, and that is made possible by introducing a concept called inner product, which is analogous to what is dot product. Yeah, we will extract the fundamental properties of dot product and make them axioms and say that any operation between vectors in a vector space which satisfies those axioms of dot product are also satisfied, then it will be called a inner product space. Yeah, so let us start introducing inner product space. Yeah, so using the concept of inner product of two vectors, which is analogous to standard dot product of vectors in Rn, we can introduce geometry concept. and we will see that these geometry concepts are very useful to analysis of data. So curve fitting and data analysis is done by using these geometric properties of a vector space, vectors in a vector space. Yeah. So towards the end, I will show that if you are given certain data, we want to understand what is the law behind that data. Yeah. So whether the data fits on a straight line or the data is fitting on a parabola or a hyperbola, etc., etc. Okay. So these problems arose in mechanics, celestial mechanics, because scientists were analyzing the orbits of celestial bodies, and they wanted to understand what is the exact nature of the orbit. And you have studied Kepler's laws. The Kepler's laws say that all the planets move in elliptic orbit. So how did Kepler, see this? So he collected data and then he tried to fit the equation of a ellipse into the data. Okay, so you plot some data and then you can guess that it is turning out to be elliptic orbit, but then you have to prove that it is really ellipse. Okay, and then you observe some more data, make predictions, and etc., etc. So natural phenomena and also applications nowadays in artificial intelligence and data analysis, we have to do a lot of curve fitting. Okay, yeah. To do curve fitting, we will see that what we are learning in this chapter is very essential. It is foundational in nature. How to do curve fitting in a data. So that I will explain after we develop little bit theory of inner product spaces. Okay. Yeah. So for now, rest of the course, we will use the field of scalars will be either real field or the complex field. And when I have A in F, we will write A bar as complex conjugate. Yeah, A bar will be used for complex conjugate. Okay, and if I have a matrix A where the scalars, the entries of the matrix are taken from this field, which can be real or complex, by A star we mean conjugate transpose. So if A is equal to Aij, then A star is obtained by taking the transpose and then take the complex conjugate of every entry in the matrix. So first take the transpose and then take the complex conjugate of every entry in the matrix, and this is called the conjugate transpose of a given matrix. Okay, yeah. So suppose V is a vector space over a field F. F could be real, F could be complex, but you fix this F. Once you say F, it is fixed. Okay, an inner product on V. Okay, an inner product on V, okay, is a rule which to every ordered pair of elements of V associates a scalar denoted by UV within these brackets. Okay, so I'm not writing U dot V because dot is reserved for usual dot product of vectors. Okay, so we write this bracket UV. This is a notation taken from quantum mechanics. Yeah, we use all kinds of inner products in quantum mechanics, and these the formula for inner product can change from one vector to another vector space. So we have this notation U comma V within brackets. So a rule which associates a scalar to every ordered pair of elements, yeah, it is called inner product if the following axioms are satisfied. So take any three vectors and take any scalar. Okay, then the inner product of U and V should be the complex conjugate of inner product of V and U. So it is not a symmetric operation. Yeah, it depends on the order in which you take the inner product. Okay, it is order sensitive. So inner product of U with V is complex conjugate of inner product of V with U, and this is called conjugate symmetry property of the inner product. Then the inner product is linear in every component. Inner product of U and V plus W is inner product of U with V, inner product of U with W. And if you use the first axiom, it will imply that it is also linear in the first component. So it is bilinear operation. It is linear in every component. Okay, when you add vectors, addition of vectors is respected by inner product. This is called additivity. Then for scalars, there are two rules. If I scale the vector v here, then this c comes out. Okay, this c comes out. So this is called homogeneity. But if I take say c times u, and then take the inner product, this will be equal to by conjugate symmetry. This is equal to v c u bar. Okay, and this is equal to c v u bar bar. This is equal to c bar u v. So if I take scalar in the first component, its conjugate comes out. So this is a consequence of this first condition and this condition, that scalars in the first component, if I scale a vector in the first component, then that scalar comes out of the inner product with a conjugate sign. Okay, it becomes conjugate. But if I scale the second vector in the inner product, then that scalar comes out, not its conjugate. The last property is VV, the inner product of V with V is bigger than or equal to 0. This is one part, that VV, the inner product of a vector with itself, is a real number, is a consequence of this axiom. Because if I put u equal to v here, then this number is its own conjugate. So it must be real. But this says something more, that this is bigger than or equal to 0. Yeah, inner product of a vector with itself is bigger than or equal to 0, and it is 0 if and only if the vector is 0. So this is called positive definite property. So there are 4 properties that we are demanding. If you have an operation between vectors, like we know addition of vectors is one operation, then I can multiply a vector with scalar, that is another operation on vectors. Now we are introducing an operation between pairs of vectors. So conjugate symmetry, that is the first axiom. It is bilinear, it is linear in every component. But then scalars come out as complex conjugates if that scalar is in the first component, and it comes out as itself if it is in the second component. Inner product of a vector with itself is always non-negative. It is 0 if and only if the vector is 0. So these 4 properties have to be satisfied with an operation on vectors, pairs of vectors. Then and only then we say it is an inner product. Okay. So an inner product space is a vector space. So already I have a set which is a vector space, and if we introduce an inner product in that vector space, it is called an inner product space. Okay, so it's called inner product space. So let us, so as I said, VV is always real. In fact, it is bigger than or equal to 0, and CU comma V, C bar U comma V. Keep that in mind. This is a common mistake in exam, that C comes out as C. No, C comes out as C bar. Okay, this way. All right, so let us look at
Didn't catch that. Could you try again?
Yeah, so let us look at some examples. Yeah, so first look at the common example of Euclidean space Rn. Okay, Rn, take 2 column vectors in Rn. They have n components. They are real numbers. Standard inner product on Rn is simply sum of xi, yi. Okay, but this can be written in terms of matrix product. V and W are column vectors. So if I take V transpose, that's a row vector, and I multiply this row vector with this column vector, I get 1 by 1 matrix, and that is precisely the dot product of V and W. Okay, so inner product of V and W I am writing as V transpose W. Yeah, so to avoid all these xi, ya, yi, etc., this is a compact notation that if I regard V and W as column vectors, then their inner product, the standard inner product, which we call dot product, is V transpose times W. So it is written in terms of matrix product. Yeah, let's look at another example. Yeah, in Cn, now my vector space is complex vector space Cn. Okay, then inner product of W, these are now vectors with complex components, and we just copy this notation, V transpose W. So the role of V transpose is played by the conjugate transpose. So V star, Okay, V is a column vector, V star is a row vector. How to get V star? First make this as a row vector, that is take the transpose of V and then take conjugate of every entry, that is my vector V star, and then multiply this row vector with this column vector W, and this is summation xi bar vi yi. So this is the inner product in Cn. Cn thought of as a complex vector space. Okay. Now let's relate it with what we already know. So in particular, suppose I take n equal to 1, then it is simply the set of complex numbers. The set of complex numbers over itself is a one-dimensional vector space. Yeah, it's a one-dimensional vector space. So suppose z equal to x plus iy. That's an element in C1. C1 is same as C, and we know that absolute value of this complex number is square root of z bar z, but z bar z by our this definition of standard inner product in Cn is simply the inner product of z with itself. Okay, so z bar z is x minus iy, x plus iy, and that is square root of x square plus y square, and that is the absolute value of z. Okay, so therefore absolute value of a complex number is simply square root of the inner product of that complex number with itself. Okay, standard inner product of Cn between two vectors v and w is v star of w. Okay, and it is copied from the dot product in Rn. So Rn becomes a inner product space, and Cn also becomes an inner product space. You can go back and check those 4 axioms which I wrote. Yeah, 4 axioms have to be satisfied. Yeah, it is bilinear, then conjugate symmetry, and then it is positive definite and homogeneity. Okay, so those 4 axioms can be checked for both these operations and see that V transpose W or V star W, they introduce an inner product in Rn and Cn, so they are inner product